Okay, so let's do this, play the same game here for the Hilbert transform on the real line. Okay, so remember that it actually had a fairly similar definition. By definition, it was HF is, get rid of this hat here. Definition was the inverse Fourier transform of this here. For L2 functions, at least, take Fourier transforms. This is probably the more common way to define it. Just the Fourier transform of the Hilbert transform is basically, by definition, the Fourier transform of f except for a sign. So it's maybe a bit silly. Sine of x, f hat of x. Okay. All right, so we're going to work backwards. So doing what we did for integrals is kind of tricky, kind of in the direction we did. So we're going to basically work backwards, and this is quite a bit more not difficult, but maybe this requires more ingenuity, and it's really beautiful stuff. I don't know who first did this. I should find out. So let's define h epsilon n to be this integral here. And it's, I apologize if this is going to seem anticlimactic at the end, because what we're going to basically be doing is letting epsilon and n, epsilon go to 0, n go to infinity. And that's basically what the Hilbert transform is going to be. So it's going to be very similar to this here, except instead of cotangent, it's going to be, well, yeah, it's going to be like 1 over pi t essentially, except for the pi. Well, actually, sorry, there is a pi. So, okay. Okay, so, and the reason why we're doing this is, the claim is going to be that when I take the Fourier transform, I'm almost going to get the sine function. And particularly when I let epsilon go to 0 and let n go to infinity, I'm basically going to get f hat of x sine x. Okay? And it's kind of remarkable that the simple convolution does the trick. And this is convolution. It's convolution with this function here, which is, this is, so let's say f is an L1 intersect L2. This here is an L whatever you want. For fixed epsilon, for fixed n, well, it's bounded. It's trivially bounded, and it's 0 off of a set of finite measures. It's 0 if y in absolute value is either less than epsilon, or less than or equal to epsilon, or bigger or equal to n. So this is certainly in L1 intersect L2. So by the homework, which I will grade very soon, I apologize for that. Sorry about that. Just want to make this a little neater. Right, everything is L1 intersect L2. So we can do, we can take the Fourier transform of h epsilon n. And it's just a Fourier transform here times this Fourier transform. And so I should mention the pi here. It will be apparent why I want a pi here in a moment. So let's figure out what this Fourier transform is. Okay, let's call it star, 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 because I already used star and star, star. Okay, well, just definition. Okay, well, this is a characteristic function, no subtlety here. So we're integrating over the set here. Y is y. So because this is an L1 function, there's no subtlety in Fourier transform. It's given by the integral definition. Okay. So this kind of, so I should mention, this is kind of analogous to, in some sense, this R parameter we had before, in that we just need parameters so that subtleties with convergence and with, issues we don't want to deal with all just go away, and kind of like, well, we'll deal with them later in some sense. And in the case of what we did before, dealing with it was pretty easy, thanks to this trick of, thanks to this trick here. Yeah, sorry about that. Thanks to this kind of trick here that this is 0, dealing with R, it was actually judicious to worry about it later, and not worry about it. Same thing here. We're not going to really worry about epsilon and n. We'll deal with it later. Okay, so anyway, enough of that. Yeah, so this is going to just be this integral here. Not much more we can do at the moment. There's really, well, in some sense, there's not all that much you can do. So let's just do something fairly trivial, and that is, let's essentially do a substitution, u equals minus y, or really y maps to minus y. Now this is really magical almost, and it's only thanks to this y that we actually get a minus sign here. Without the minus sign, we'd be screwed. We'd be really screwed. But thanks to this y in the denominator, we get a minus, and just check this, it's pretty easy. This is really 2 integrals, so we're really doing 2 substitutions. Okay, so what does this do? Well, this says that if we add this up twice, to, take this, whoops, sorry about that. Really should never try writing without a digital pen. There we go. So we take this plus this here is going to be 2 times star, star, star. So divide by 2. And to make life a little easier, I'm going to factor out a minus. So this would be the minus here. This would be plus here. Okay, why do I want to do that? Well, the reason why I want to do this should be pretty obvious. Just write out these exponentials, and this is going to be minus I. Well, you really get a 2i here. I mean, it's 2i times the imaginary part of this. So it's 2i sine. Well, that's, sorry, the 2's cancel and you get the I here. That's why you get the I here. So it's sine 2 pi xy over y. All right, so let's continue on and see how we go from this expression to the sine function. This is going to be extremely easy but subtle. So we're going to have to be a little careful. And so I'm going to go through this, even though this is literally like Calc 1, easy Calc 1, actually. So I'm going to write this out as 2 integrals, and I'm going to do a substitution. So first, let's do different cases. Let's say case 1 is x is positive. So what I'm going to do, sorry about that. So I'm going to write u is 2 pi x, and then 2 pi y. Okay, so du is going to be dy, really not much there. Just find du, divide by u, you get dy over y. So when, 1 second. Okay, so when y is minus n, u is minus 2 pi nx. When y is minus epsilon, u is minus 2 pi epsilon x. Same thing for this integral here. Okay, but sine u over u is even. Okay, so I can really just rewrite this as 2 times this integral here. Okay, but really absolute value of x is x. So this is 2 times just this integral here. And I'm writing absolute value of x because for x negative, I want to get basically the same integral except a minus sign. And that is how the sine function will pop up. Okay, so, well, case 2 is not very interesting. X is 0. What happens when x equals 0? Well, what's sine 0? 0. There's no subtlety here. This is a Riemann integral, a Calc 1 Riemann integral, because everything is nice and continuous. We're over a finite interval for fixed epsilon. You take a Riemann integral of 0 over an interval, you get 0. So not interesting, really. Now, case x is negative, we have to be a little careful. So what am I going to do here before I do anything? Let's say u is minus 2 pi y, and again, du is dy over y. Okay. So you don't get a minus sign from right. So you don't get a minus sign from here, but what you do get is sine 2 pi y is minus, and this is crucially important, minus sine u. So I can't do different colors, but if I did, I would circle this minus in 5 different colors because it's super, super important. And then the same thing here. Okay, so we get this minus sign, that makes this a plus. So there is no minus sign here. Okay, well, let's just be careful with the limits of integration. When when y is minus n, u is minus n minus 2 pi x. That's great because x is negative, minus 2 pi x is positive. Same thing here and same thing for these two. Because x is negative, there's no issue, we don't have to switch anything. And in particular, we get the same integral. Well, again, sine u over u is even. So it's really 2 times the second integral, which is the same thing if we had absolute value of x, because absolute value of x, when x is negative, is minus x. Okay? So again, this minus here, which is super important. So I can't fit another exclamation mark, but this minus sign here is what gets rid of this minus sign here to get a plus sign. So the conclusion, and it's actually good that we get 0 when x is 0, because sine of 0 is 0. So the conclusion is that the Fourier transform is minus 2i sine of x times this integral here. Okay? All right, so I don't know why I have epsilon here, but anyway, that's just an x. That. Okay, so let's just continue on. Well, we know that this here is the Fourier transform of this function here times Fourier transform of f. Again, assuming f is L1 intersect L2. We only care about Schwartz functions, so certainly L1 intersect L2 is fine. Okay, so the easiest thing to do now is to use our L2 theory to get pointwise convergence results. It's just, we have good solid L2 theory. Let's use it to make life easy. Okay, so use the fact that the Fourier transform is a L2 isometry. So what I'm really doing is taking the Fourier transform of this whole thing. Whatever. Right, so you have really a common sine function. So it's really instead of 1 here, it's sine, and let me stick a sine here. And remember, you have a common I. It was minus I. What did I say? Yeah, there should be a minus I here. Sorry about that. All right, so remember, yeah, sorry, the Hilbert transform is minus I times this here. Right, so you're also factoring out the minus I, so if you really want, minus I. Right, so you can factor out this common minus I sine x. Almost everywhere sine of x is 1. It's 1 except at 0, so no issue there. Okay. So certainly in L2, you can use dominated convergence theorem to get that as epsilon goes to 0 and n goes to infinity. Well, this whole thing here is just 1. As long as x, again, for almost every x not 0, that implies that this limit here, and I'll be a little more precise in a second, doesn't really matter how we take this limit or how you interpret this, but 2 over pi 2 pi epsilon x. Doesn't matter if x is positive or negative. Well, really, there should be no subtlety in evaluating this integral. Good. Glad I have room. Well, this is just 1. And that's why we had the 1 over pi from the very beginning. This whole integral here from 0 to infinity is pi over 2. Pi over 2 times 2 over pi is 1. Okay? And there's really no singularities. There's no issues. You know, sine 0 over 0, or as y goes to 0, sine y over y goes to 1. So, so yeah, really, if you want to, you can define any sequence of epsilons and n's. Epsilon goes to 0, n goes to infinity, and you'll get that. So, yeah, so in other words, for a subsequence of these epsilons and n's, you get almost everywhere convergence thanks to L2 convergence. We know L2 convergence implies almost everywhere convergence for a subsequence. Okay, right. All right, so let's put that to good use. So let's right. So we know basically for sequence of epsilons and n's, we know that h epsilon n. So let me just write this out. So here I mean little n goes to infinity. N goes to infinity. Sorry, infinity, not 0. And so this might look a bit convoluted, but there is certainly hope. And as long as f is an L1 intersect L2. Okay. And this is 100% rigorous. You know, really pick any epsilon n go to 0. Pick any n of n going to infinity. We have L2 convergence as n goes to infinity. Hence, there's a subsequence that converges almost everywhere. So, sorry. Okay. Now, what we're going to do is, for a Schwartz function f, we're not going to find almost everywhere convergence. We are going to find point-wise convergence. And there's, this is what I love about this kind of subject matter. You're using abstract functional analysis, abstract LP theory, and then at another moment's notice, just everything is super concrete. Just like before, we're going to get to the point where like all these limits are going to clearly exist point-wise, because there's not going to be any subtlety. Okay, so what do we do? How do we get to that point? Let's do a trick similar to what we did for Fourier series a moment ago. So sorry, this is a bit messy, but so again, this is Calc 1. This is like 2/3 into Calc 1. You integrate 1 over y, you get absolute ln of absolute value of y. You do this integral here as long as epsilon is not 0. If epsilon is positive, no matter how small it is, I don't care if it's 0.000000001, just do the Calc 1 integrals, you get 0. Okay? So what does that mean? So let me actually go to the whiteboard. Sure, let me go to the whiteboard real quick. All right, so maybe black here so it's a little easier to write. Sorry about that. Okay, so h epsilon n f of x is going to be this integral here. Epsilon is less than y is less than n. Let's assume n is bigger than 1. It's not a, obviously we can assume that. We're letting n go to infinity. So this is going to be integral epsilon less than y less than 1. Whoops. Plus this integral here. Whatever, doesn't matter. Okay, so now I'm doing that trick here I just had a second ago. This integral is 0. So really I want minus f of x. And here, now I'm going to assume f is Schwartz. So it's point-wise defined everywhere. There's no issue. So this is 0. So this is equal to, no limits, no magic, whatever. This is equal to, period. It's no subtlety whatsoever. No, it's as mathematically pure as you could want. This is equal to this integral here. And you should be able to see why I'm doing this and where this is going, what the punchline is. Okay, so For a Schwartz function, if we let epsilon go to 0 any way, how, shape, form you want, we get a perfectly well-defined Riemann improper integral. Because there's an issue with y equals 0. Here there isn't. When y is near 0, f is differentiable. So this is an absolutely bounded function for y near 0. It's just when y approaches 0, it's f prime of x. There's no issue with things out to infinity. There is no out to infinity. We're stopping at absolute value of y is less than 1. Sorry, I forgot to. Okay. So there's no issue with letting epsilon go to 0. I don't care how you approach 0. I don't care in what order you let epsilon go to 0, or do you do that first, do you do n first? I don't care. This goes to an improper integral, 0 to 1. That's well defined. Same thing here. F is a Schwartz function. So this decays faster than any polynomial. So this is a well-defined improper integral as big N goes to infinity. There's no issue with the y in the denominator because y in absolute value is way far away from 0. It's bigger or equal to 1. And I guess this should be, not that it matters, but this should be less than. Okay, so yeah, no matter how, way, shape, form, you let epsilon and n go to 0 and infinity respectively. For a Schwartz function, we have rigorously shown that you're going to get this quantity here, which is absolutely well defined as 2 improper Riemann integrals. Okay. Now, what you could also do, you could actually write this. Now you can write this out as, just take this integral here. Kind of separate, completely, maybe I should do a delta or whatever. Kind of separate of anything here. Just forget about anything we've done up to this point. We have these 2 well-defined improper Riemann integrals. No subtlety whatsoever in their definitions, because f is a Schwartz function. And I do want to emphasize this, what I'm doing has absolutely 0 meaning unless f is a Schwartz function. And that's why, in this area, Schwartz functions are so useful. And so, they're very useful. This has no meaning when I'm doing it. It miserably fails unless f is a Schwartz function or a nice enough function. L1 intersect L2, obviously not. Nice enough, we need differentiability. And we need very fast decay. Anyway, so enough of that. Yeah, so there's no issue with just saying that this integral here is going to be this limit. Again, there's no issue with everything's nice and bounded because f is differentiable. So why not? Well, now here, what we could do is we can still, again, use this fact here to get rid of this minus f of x over y. You can't do anything with this limit. You literally can't. Even if f is a Schwartz function, the only thing you could do is evaluate this limit to get this here. But in general, you really just can't do anything. And this is really often what's called the Hilbert transform. So for at least a Schwartz function, we have the Hilbert transform is defined as this integral. So the nice part about this is, at the very least, you want to call this h epsilon f of x. Well, this is obviously defined for any f in, yeah, as long as f is in L1, this is really defined. So as long, yeah, so You can define this for a much wider class of functions and Schwartz functions, H epsilon at least. But all right, so yeah, our goal really is to take this here and prove this limit here and prove LP bounds for this when f is a Schwartz function. And that's basically going to be the rest of the course. We're going to develop the very powerful tools, particularly maximal functions, Hardy-Littlewood maximal function, Marcinkiewicz interpolation theorem, Calderon-Zygmunt decomposition. So things are going to get a bit more, they're going to get quite a bit more technical, but that's just the nature of the beast, really. So, all right, hopefully this is a bit long, but yeah, I think it's tough to find really super clear discussions of all this. So hopefully this was interesting, made sense, and all right, so long until next time.